Let's do another example where we find the critical numbers of a function and we also find the absolute max and minimum values. So this is the function I'm going to be looking at. It's f of t is equal to t times the square root of 4 minus t squared. And on the interval 1, 2, which is a closed interval. So the first thing I'm going to do is I'm just going to rewrite my function in a form that's a little easier for me to take the derivative. So I've just written the square root of fractional exponents. And this means the derivative, using the product rule, is t times the derivative of this guy, which is 1/2 times 4 minus t squared to the negative 1/2. And we can't forget the chain rule. The derivative of this portion is negative 2t. And then I'm going to add, okay, that's from the product rule. And I'm going to take 4 minus t squared, and I'm going to multiply by the derivative of this function, which is 1. So let's just clean this up and rewrite it a little bit. I can cancel these 2's. And I can rewrite this with the square root again. So I end up with negative t squared over the square root of 4 minus t squared plus the square root, there should be a 1/2 here, plus the square root of 4 minus t squared. So in order to find the critical numbers, what I want to do is I want to find the values of t in the domain of the function such that either f prime of t is undefined or f prime of t is equal to 0. So the first thing I'm going to do is I'm going to find the domain of this function. And recall that one of the issues with the domain is when we have a even root, we need to make sure that this quantity is positive or 0, can't be negative. So we need that 4 minus t squared is greater than or equal to 0. So in order to solve this inequality, we're first going to, it's called a quadratic inequality. We first figure out where it's equal to 0, and that happens at 2 and at negative 2. And then we just test the values in between. We pick a number in the 3 intervals and we test that number. So for example, if I pick negative 3, I can see that this will be positive and this will be negative, and therefore my inequality is false there. However, if I pick, say, 0, then I can see that this quantity will be positive and 2 plus t will be positive. So the inequality is true. So I'll have a true there. And now if I pick a number like 3 over here, I can see that this quantity will be negative and this quantity will be positive. So the product will be negative and the inequality is false there. So that's not going to be part of my domain. So 4 minus t squared is greater than or equal to 0 on the interval negative 2, 2. And that, so that is going to actually be the domain of my function. So the domain of f is negative 2, 2. And this also implies that f is continuous there. So we'll use those important facts later. So one thing that you should note is that our derivative is not defined at t equal positive or negative 2 because the denominator here would be 0. But those are the only points that are in the domain here, such that my derivative is not defined. So t is not cannot be equal to positive or negative 2. Now, in order to find the values where f prime is equal to 0, I need to solve this equation, and I'm going to do that by clearing this fraction here. I'm going to multiply both sides of the equation by square root of 4 minus t squared. And that will eliminate the fraction. So let's see what happens when I do that. I have, and of course I'm assuming t is not equal to positive or negative 2 because, you know, then this quantity would be equal to 0. So now I'm going to multiply the left-hand side, or the right-hand side by 0. And what this leaves me with is negative t squared plus 4 minus t squared is equal to 0. And if I solve this equation, I have 4 minus 2t squared is equal to 0, which implies that 2 minus t squared is equal to 0, or in other words, t is equal to positive or negative the square root of 2. So those are the values, and I check those values are in the domain of the function. Root 2 is approximately 1.4, so those are in the domain of my function. So the critical numbers that I have so far, let's just write them down. The critical numbers are t equal positive or negative 2 and positive or negative square root of 2. Okay, so now let's do the second part of the question. Let's find the absolute maximum and minimum values of this function. So if you recall in part A, we found that the critical numbers were positive or negative 2 and positive and negative root 2. So once again, we're going to use the extreme value theorem and the closed interval method. So the extreme value theorem tells us that if our function is continuous on a closed interval, so in this case, the closed interval we are looking at is the interval 1, 2. And we know that the function is continuous from our work with the domain on the interval negative 2, 2. So it's definitely continuous on this interval. It's continuous from the left at 2. And then the function must attain its absolute maximum and minimum. So the closed interval method, remember, we find the critical numbers. We already did that in part A. We evaluate the function at each critical number and also at the endpoints. So for us, that would be 1 and 2. And then we just, the largest value will be the absolute max. The smallest value will be the absolute minimum. So let's go back and do that. So step 1, so really this was our step 1 for the closed interval method. So step 2, okay, we are going to evaluate the function at, let's start with the endpoints. So f of 1 would be 1 times the square root of 4 minus 1 squared. So that's root 3, that's about 1.7. And I'm going to do the other endpoint, f of 2. That's also one of the critical numbers. So I have 2 times the square root of 4 minus 2 squared. That's just 2 times 0, or 0. Okay, so that takes care of these 2 points. And if I look at this interval, the interval from 1 to 2, the only critical points, I don't have to worry about the negative critical points. We already did positive 2. I will also have to input a root 2. Okay, so that is actually the only other critical point we haven't done yet. So f of root 2 is equal to root 2 times 4 minus root 2 squared. So that is root 2 times the square root of 4 minus 2. So that's just root 2 squared, which is just 2. So the closed interval method, our step 3, it immediately just tells us that this is our absolute max. On this interval, 1, 2, and our absolute minimum is 0. Okay, so f of 2 equals 0 is our absolute minimum, and f of root 2 is approximately 1.4. So let's check our intuition and see if these answers match up with, or match up with the graph. So let's graph them. Okay, so here is the graph of our function, and you can see looking at the graph that the domain of the function is really is negative 2 to 2, and you can also see the function is definitely continuous on that interval based on this graph. Now, if I look specifically at the closed interval going from 1 to 2, I'm just going to zoom in a little here. Recall from our calculations, we said that the absolute minimum value of the function was 0, and it occurs at 2, and you can see that, yes, that indeed is the absolute minimum value. And we also found that at f of root 2 equal 2 was our absolute maximum value. So I'm going to... this point appears to be the absolute maximum on that interval, and as you can see, these numbers are rounded, but you can see about 1.4, that's root 2, that yes, we do hit a absolute maximum value of 2.